LC. Well, what the heck is LC, Jamesa? What's that? Liquid chromatography. Yeah, liquid chromatography. All right, so you can quantify with it. You can find out what things are. I guess pretty much depends on what your goals are. And here's a bunch of goals, right? A lot of things are described above. But can you see one, Pedro, that looks like it could have been done with the GC and just as well? See an example up here? What's something that could have been just as well with a GC? Chemical, what's that? Which one? The fourth one? Chemical. Well, that doesn't even do anything. What is that? I'm not sure what that means. Pick one that kind of, they're doing something. I was a little quick writing this, I guess. What's another one? Sometimes more of a story behind it. Let me pick one for him. Identify confiscated narcotics. Okay? The reason why I wanted him to pick something is because then I can say, whoa, maybe not. Why? Because if it's going to be on the GC, your analyte has to be in what phase? Gas. You try to heat it up in the, what is it called? When you inject it, starts with an I? Inlet. You try to heat it up and get it to vaporize. What if the thing does what? Breaks down. That's the word we're not supposed to. We're supposed to use what? It starts with the D. Break it down. It's called decompose. It's falling apart. It's decomposing. Then you're not going to analyze that narcotic anymore. You're going to analyze its burnt offering, right? It's not going to be able to figure it out. So that's not the situation with LC, though, right? Liquid chromatography, if you're going to buy an instrument, dang, you should be buying a liquid chromatograph. Okay, and we're going to be talking about why, but so why have an LC? Because you can do everything on it, right? Every compound known to man, I don't care what it is, can be analyzed on here, right? Whether it's a gas, liquid, or solid, we can get them all to work. Not so with GC, right? And here's a big flow diagram of the whole system, how it works. But let's start at the beginning in 1906 with Sweat. Okay. Sweat. That's how I pronounce his name anyway. He took, just like Galileo, I don't know how these guys, what possesses them to do what they do, right? This guy's walking around the forest or whatever he lives, and he sees the little colors in all the different trees. So he makes the conclusion, which even I, all those colors must be in the leaf. Otherwise, you know, how could it all be there? And we know the term starts with the C. What are those colors? Chlorophylls, right? But hey, how does he make that? To me, that's a leap right there. To understand that all those different colors are all in that leaf at the same time. But he did it. Right? And he says, well, hey, I'm going to try to get those colors out. Again, what possesses people to do this? This is tough. Anyway, he took a column, and he smashed in there. I'm sure he tried a lot of different things, but the one that he got to work, what is this? Casey, what is this stuff? Yeah, you got to say, we're supposed to be budding scientists. This is what compound? Carbonate. What kind of carbonate? Calcium carbonate. He took chalk and he ground it up. Calcium carbonate, he ground it up. So that's what he used as a stationary phase, right? He used chalk, but we're not supposed to say chalk, we're supposed to say calcium carbonate, right? Well, fine, you like chalk. Okay. Now, chalk, calcium carbonate, is a very what, Nyla, type of compound on the polarity scale? It's definitely not organic. It's inorganic. But look, it's calcium ions and carbonate anions. This is about as polar as you can possibly get, right? These are ionic compounds. They're salts. They're very polar. Okay. Now, just to get in some terminology here, whenever we use this type of stationary phase in liquid chromatography, you're supposed to call it what, Kimberly? What would you guess? Which one of those? They started out with it, so it was the typical thing, normal. Right? Okay. So anyway, that's what he did, and he filled that thing with chalk, and then somehow they knew that they're playing around with this stuff. He's not all inventing this all himself. Who the other dudes were, but petroleum ether they had available. Stick some leaves in petroleum ether to get the green gooey extract stuff. All the colors must be there, he figured. He dumps it all up on top, right? And then he just keeps dumping petroleum ether on the top. So that's his mobile phase, right? Flows on through the chalk, and he starts getting the individual bands. As long as he made his tube tall enough, I'm sure he had to do this multiple times to figure it out, but he got the pure chlorophylls, right? So he's the dude who really started this all off. So in the 60s, liquid chromatographs came out. Sweat did liquid chromatography, but he didn't do HPLC. He just did the LC. What's the HP part, Jeff? What's HP stand for? Does anybody know? No. High performance. It shouldn't be high performance, but high performance sells more. It should be high pressure. That's what it should be, but it's high performance. I guess it's, it sounds better for sales and things, but it's high pressure. That's really all you're doing. At the head up here, how could sweat have really saved a lot of time and energy and effort? Well, heck, I'm sure they had bikes, right? Bike tires and little, right? Little bike tire pumps. That's all he had to do is hook that up to the top, right? Have a little rubber inner tube up there, pump up the tire, just put some head pressure on there. That would push everything through faster. He'd have to pop it off every once in a while and keep putting petroleum ether on top. But he could do that. He would have had an HPLC. Okay? Is that okay, Miranda? Yeah. So that's all he needed to do was to add some pressure, some head pressure up at the top of his column. He would have had an HPLC. Okay, here we go. This is why, if you only have 40 grand, and this is the instrument you'd buy, is an LC. Because only in the GC, out of all the compounds known to man, it's only 20% you can use on the GC. And why do you think that is again, Pablo? You can't trim it without what? You can turn anything into a gas, but without decomposing. It's got to be in the same molecular structure in that solid or liquid phase that's a gas phase. And that's not always. Look at sugar. Try to vaporize sugar. It ain't going to happen. Right? Aspartame. A lot of those fancy, a lot of drugs. Other drug compounds too. Vitamins. LC manufacturers spend a lot of resources to make their liquid chromatographs ultra low volume in order to minimize. Erica, how would you fill in those blanks? Now this answer would work, but it's not technically right. We're supposed to use the right jargon. Fat peaks. I just thought of that. That's how it works. That's two blanks. And that's exactly what they want to minimize. But we're not supposed to say that. We're supposed to say, what was the word we used? There's two types of diffusion. Eddy and longitudinal. Okay, they both contribute to, there's the Z, zone broadening. That's what goes in the blanks. Zone broadening. Okay. So, what is the difference between isocratic? Doesn't matter whether you're talking about GC or LC. We can do these elutions. And when Mr. Sweat there, Cat, was dumping petroleum ether up on top of his column, okay, was he doing a isocratic or a gradient elution? Gradient. What's the difference? Isocratic means, well, one, everything. I mean, you can't change anything during this whole elution. when you're separating all these little bands out on the column, you can't change anything. That is a what type of elution? Isocratic. You change one little thing, all of a sudden now it is gradient. So he was using isocratic. However, there's so many things Sweat could have figured out. What if, I don't know, the little green dude, he's chlorophyll A, right? Let's say the green guy, the green band. Well, I have red now. What chlorophyll is red? Anyway, let's say the red is just hanging in his little chalk column, right? And it just wouldn't come out, wouldn't come out. But this petroleum ether he's wasting. Well, instead, he could change his mobile phase, his solvent, to something like dissolves like, something that would dissolve that red chlorophyll even better. So if he did that he would have done a gradient elution.
Only changing the mobile phase?
Anything. You can change any parameter, flow rate, anything you can imagine. What are parameters? There's flow rate. What's another parameter? Temperature, pressure. You really can't change columns, right? Because then you'd lose everything. But I think those are the main ones. Okay. How is a gradient elution performed in LC or GC? Now, this whole idea of performing gradient elutions, that's really, we're going to do chromatography. That's all what they're talking about. We want to separate these compounds. You have to change stuff to do it. You can get lucky, set everything up, and just do an isocratic run. Maybe you get lucky, but odds are you can get co-eluting peaks, and it's going to be, or it takes forever. You're going to have to mess with things. So what do you mess with in an LC to move these little peaks around? And what do you have to control? Mobile phase. More specifically, the mobile phase, what makes it up? What's the technical word? Starts with a C. The mobile phase. Go ahead, composition, right? Constitution, same thing. The mobile phase composition. What makes up the mobile phase? That's what you have to control over here. What do you have control over with the GC? To move these peaks around.
Isn't it the same with temperature and so much?
Well, the whole thing in a GC is located inside a oven, so definitely you have temperature. So you could mess with temperature. Can you mess with anything else? What's that? Oh, yeah, but they have to pop the whole thing out, right? Because we're talking about during a run, you're going to change something. So you really can't mess with column length. There's not a whole lot you can do. And maybe flow rate, that you could mess with. But temperature is the biggie for GC. And what's the biggie for LC? Mobile phase composition. There you go. Okay. What are the major things you've got here? Okay. So you have a whole bunch of bottles over here. All right, and they're all connected. Okay. So these are all just a whole bunch of different solvents. You can call it methanol, water, who cares, whatever you want to put in there. Pure solvents in different bottles. Okay, so these are your solvents. And then what you're going to do is the computer, he's going to say, you don't want to have the computer do all this. Let's suck up 80% of this ethanol and 20% of the water. Or let's do 80% of that one, 5%, right? Just so that percents add up to 100. And all that is done by this little guy, the solvent proportioning valve. So all we're saying is that all these LCs, all these liquid chromatographs have these things in common. They're going to have all these solvents that you can pick from. Then they're going to have something that, okay, it's going to take different percents out of different bottles. Okay. Then it's going to shoot it over to a pump. Because we don't want to do liquid chromatography, right? Liquid chromatography is like the piece of paper and food dye and just sit in some water. We want to do HPLC, so we need some pressure. So you can have a pump, okay? Now, mechanically speaking, all we know of engineering-wise, this is my pump. Right? That's all I can do is these pistons. So what happens is you would end up getting, right, all your peaks would end up looking like this. And they do. Because that's all our pump, that's all we know for engineering, to make a pump. So this next guy, we have to dampen the, they're all going to have a pulse dampener. Okay. So, all right, we haven't even injected anything yet. So we have all our solvents coming in. They're getting all nice and mixed. They're getting pushed through. Now we have a nice, well, I guess a flat line, right, hopefully. Now we're going to inject. This is where you're going to inject stuff. I don't know, you could, auto sampler. Injector is just the most general word I can think of, right? Where you're going to inject stuff. And then, now you have to have a column, right? That's going to be like dissolves like, and you're going to put whatever you want in there, whatever kind of stuff. And it's called the analytical column. It's the long one. So you finally injected stuff, and you're ready to get it separated. The problem is that this guy costs around $700 to $800, and it's really easy to clog. I don't know if you've seen what, I should have some little demonstration things. You've seen like little tiny wire, like copper wire. That's what the tubing looks like for this stuff. It's really competitive to make these nice machines. So they want low volume, minimize that zone broadening. They've done it to the extreme. To connect all this stuff, it looks like a wire. But it's their tubing. So this stuff is really, really easy to clog. Because you're injecting whatever you want. You know, there's narcotics, blood, whatever you're injecting on this machine, it's pretty dang easy to clog. And if this costs $600, no. So we're going to have a little piece, this essentially cut off, and they have a guard column. So before your big expensive analytical column is what they call a guard column. So that's what you're going to clog up. It's like $20 and then you throw it away. But it's made out of the same stuff that he is. So something's going to clog, you clog up him. Okay. Then you go to your detector. So if everything's done right, you did your chromatography right, you have pure pretty peaks coming off your column. Everything's eluted. It's really dilute, but you don't care. Things are really sensitive. You'll go to your detector. Okay. And then everything goes down to waste. Okay. So if you wanted to collect the stuff, instead of having a waste, just put in a little test tube or something. Right? You actually collect pure components. We did that for this scorpion project out here. We collected the compound that causes scorpions to fluoresce. And analyze it, try to figure out what's going on there.
What part is the computer hooked up to?
Oh, yeah, let's make little dashes for electronic. Okay, he should be hooked up. Good question. He definitely has to be hooked up to the solvent proportioning valve. He's gonna go to the pump too, right, to control the flow rates. I'm sure he has to go to that pulse dampener to make sure things turn him on and off. He has to go to the injector, otherwise you don't know when things were injected, what's the time. And there's no electrical connection to the columns. I mean, there's nothing for it to do there. That's just something you actually physically put in and out. Like a cuvette, there's no electrical connection in a cuvette. So, whoa, what am I doing? No electrical connection. But there would be a big electrical connection to that detector. Right? So the computer kind of runs it all. Okay. So all liquid chromatographs, HPLCs, have all those things in common. Okay. A common detector, the diode array detector. Okay. Well, what is it trying to do? I think this picture might be easiest to visualize. You've seen the little the solar cells, like those little calculators that especially we hand out in general chemistry, has that little brown thing up on top, that brown strip. Solar cells, right? Well, that's all this guy is. He's the solar cells, but much very sensitive. But that's what they're for. They're going to be little solar cells. And then you have something that's going to break light up into, what are the colors? Name of the dude? Roy G. Biv. Red, orange, yellow, green, blue, indigo, violet. So you're going to have some nice grading here. They don't use prisms. They use gratings. Right? And you have some white light. So forget the sample for now. Just forget him for now. Right? You have this white light, goes through a grating, and then you see Roy G. Biv spread out on the diode. This photodiode array, a whole bunch of little solar cells. So the guy right here on the end, he's always red. The guy over here is always seeing blue and that sort of stuff. So when you do put your sample in, and it does some absorbing, let's say it absorbs the red region, well, the only signal that's going to change is that red region. So you can get absorbance spectra out of it. All at once. If you did the spec 20, remember you had to change the wavelength, right, to 400 or 320 or whatever, right? Here you get all wavelengths measured at the same time. It's really, really fast. You have a big, expensive UV vis upstairs, and it's not like that. You have to scan one wavelength after the other. So there's real advantages to a diode array detector. But that's a very common one. Okay. So just what is inside the column? It's this stuff. The active ingredient in the analytical column, or the little piece before it, called the what column? Guard column, right? Protect the analytical column. So these little tiny particles coated with stuff. Okay? And the most common type of liquid chromatography, called partition chromatography, but they have a bonded phase, right? There's something bonded to these little particles. Engineering-wise, we've gotten really, 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 really good at making little tiny glass balls, all exactly the same size. So since we've got really, really, really good at that, we're going to use that and just coat it with different chemicals. Because remember, whose diffusion was it where if these darn particles are different sizes, you get different paths? Eddy, right? So you want to minimize that eddy. And you want all these particles the same size, get uniform packing and all that, so we can minimize eddy diffusion. So that's what they've done. And what is glass? SiO2. It's a crystal, right? SiO2. But you have all this stuff is silicon, oxygen, right? Silicon. Okay. I drew too many, but you have to draw a crystal out. And so you start out with your little glass sphere, and that's the little particle. Okay. Now here it's a total secret. They don't let anybody know how they did this, even though you can kind of figure it out. But because we'll tell you why in a little bit. So draw those exact same silica guys. All right, and then you have these O's. But I'm not going to draw the H's on all of them. Right? They're all bonded to, I don't know. The most common is a C18 column. So I literally have to draw, right, 18 carbons on here. Right? I don't know. On the end, right, CH3. You have to put all your H's on there. These are really long, big things, right? If you do that for all of these, except leave one of these uncovered. So 18 carbons, all those hydrogens and everything. That's a lot to write, but just so you get the idea. And one more down here. I'm not even counting. I'm just putting a whole bunch on there. Okay, I'm trying to make a C18 column, though. Should have made it something easier, but this is the most common. Patented process. But they can't get them all. And this is where all these big companies like Supelco are competing, because this is why it's hidden, because some dudes are doing better than others. Okay? But what are we trying to answer? In this type of chromatography, the stationary phase is chemically bonded to a glass bead, I guess. Glass bead, glass ball, whatever you want. A glass sphere might sound better, right? Okay. Now, what's the question here? Okay. We want pretty peaks, but instead of getting a pretty peak is nice, sharp, perfectly symmetric on both sides. But sometimes you can get some tailing. See if I show you what I mean by that. Right? And getting area under the curve, you saw that with the GC. Chromatograms are chromatograms. You're after the area under the curve. More area, more signal, more stuff. So this is more difficult to integrate with this tailing. And you have to, right, it'd be easier for things to co-elute and peaks to overlap. Yes?
How did it get broader?
Okay, we're not there yet.
Oh, yeah, it's like,
On your above, so we sketched the bonded phase particle, circle the region that leads to peak tailing. It's going to be the OH. It's going to be the OH stuff. That's why it's such a big deal to get rid of it. But you can't get rid of them all. It's really tough. Okay? So you're going to, but this is how you sell your columns. Remember, they're expensive. This is how you sell them. Make these pretty peaks. So you got to do a really good job covering all those OHs. A blank stationary phase is referred to as reverse phase chromatography. Anna, what would you guess? A what? Non-polar, right? Because before we said normal was polar, so non-polar. Right. Like dissolves like. And that's all we're interested in. We're all interested in these organic compounds. Drugs, every compound you're interested in nature, all these pesticides, every environmental analyses, vitamins, biochemistry, it's all organic stuff. So like dissolves like. If you want your stationary phase to interact, let's make it really nonpolar, very organic-like. A lot of carbons. And some general LC ideas. I remember when we first got the machine here, I wasn't especially trained in it, but I had common sense. I mean, the guy who came to install it didn't. He actually took one of, pretend this is our column, and if nothing goes through, you get high pressure, everything shuts down. So we're getting high pressure and everything's shutting down. So something's got to be clogging. So he takes the analytical column apart, pops it off, and oh, look at all this white shit in here. He takes his paper clip and he starts digging in there. Well, what is he digging out? Yeah, the packing, that stationary phase. And then, so he goes, well, I should fix it. So that's something that would destroy an LC. That's not on the list here, but okay. So you got to be careful at low and high pH, but other than that, you're okay. So you can read through those, but benzene. Benzene is injected. Now, if you can answer this question, I think you're really following along here. Benzene is injected onto a C18 column. Then, using the same separation parameters, not changing anything, is injected onto a C8 column. Sketch how these chromatograms may look. So I'm going to give you what benzene looks like. Benzene is how many compounds? How many compounds? How many peaks should I see? Just one. It's one compound, right? So I should see one. So we're going to make it a nice pretty peak. And I'm going to say 5 minutes. Just making it up. Okay? You change columns to a C8 column. Sketch in what you think it's going to look like. And just guess what you think the time would be. No changes, write it exactly the same. Remember what you're changing and what effect that's going to have. Let's pick on Miriam. How many peaks did you draw in the C8 answer? Good. She just drew one peak. Kathleen. So I'm going to draw one peak. Well, where should I draw it, Kathleen? If this is 5 minutes, where did you draw it? Right at 5 minutes, faster or longer? Huh? Longer? Over here somewhere? Or she just drew it big and fat? She just drew it big and fat. Okay. She said she did. Anybody do anything different? I hear faster. Now, the only way to get this tailing or to make things fatter is to either mess up the packing, have a lot of those little OH guys there, or change the flow rate or screw something up. So it's the exact same parameters. So we should have roughly the same peak width, the same zone broadening, because we're not really changing anything. Assuming that the C8 and the C18 column are both good, expensive columns that are evenly packed and everything, our peak width should roughly be the same. So that shouldn't change on us. What's going to change is either it's going to get faster or slower. Faster. Why is faster right? Is that right? All right. Yeah. Why is faster right? Because inside, just remember, like dissolves like. And what these guys talk about a lot is, ooh, that compound's really organic, or he's not as organic. All they're talking about is the number of carbons. So if some compound has a lot of carbons, oh, that's really, really organic. So keep that in mind, along with the idea like dissolves like. So which one dissolves benzene better? C18 or C8? C18. Because what's benzene? Benzene's an organic compound. So the more organic your stationary phase is, the more it's going to dissolve in there. But that's not the word we're supposed to use. We're supposed to use the word, it's just an R. The more it's retained. The more it's retained, right? So with C18, I mean, that's really grabbing on and holding on those organics. In fact, if you have a whole bunch of peaks, the very last one that comes off is going to be the most organic out of all those guys. And that's something that you get used to saying. The most organic out of all of these. Well, that just means he's got the most carbons. So since benzene is an organic compound, we're making the stationary phase less organic. He's going to come off faster. He's not going to be retained as well. Okay? So I don't know, anywhere in here. Okay, it doesn't really matter where. Okay, another question. Using a C18 column, a sample of gasoline was injected into a liquid chromatograph using a mobile phase of 45% ethanol. Liquid chromatograph. Here's your mobile phase. 45% ethanol, 55% water. Column temperature of 30. Can this chromatogram be improved? If so, specify how. Okay, let's make this more dramatic here. Put a little guy there. This is 59 minutes. Here's 5. So is there room for improvement, Casey? Yes, most definitely. Okay. Hopefully you agree, Pedro. Yes? He does. Okay, Amanda. How do you fix this then? What could you do? Raise the temperature. Okay. Do you want to raise the temperature at the beginning or when? Okay, more specifically, where? I would say after 5 too. Because if you go any earlier, right? Because remember with oh, is this LC or GC though? This is LC. So raising the temperature will help, but not a whole hell of a lot in LC. GC, dang. GC after 5, I wouldn't, GC, if it was GC, 5 minutes is the answer, right? Dang, you just crank it up after 5 minutes. But don't screw it up earlier, because these guys are going to start coming out so fast, they're going to be on top of one another.
So then just change the percentage.
Okay. I got to change the mobile phase composition, Adriana. How are you going to change it? So after 5 minutes, we're going to change the mobile phase composition. How are you going to change it? What percents would you pick? You'd pick what and what?
I pick a higher percentage of ethanol and a lower percentage of water.
Is she right? Remember, like dissolves like. This stuff it's what type of column? C18, a very organic column. So the guys who come out last are the most organic. So, and which is your most organic solvent here? Ethanol. So crank him up to what? I don't know. That's what the chromatography is all about. You guess. You throw in, just increase it. Right? I'd really bump it up high though. Right? After 5 minutes. Make sense? Okay, so we have to write next to each one LC, GC, or both. So let's just start with number 1. We'll start in the back with Adrian, and then we'll just keep going. Analyte may decompose upon injection. What's that? Both. Now, if you answer both, is there a place for my, here's Elsie, is there a place for my little sample to decompose? No. Right? You're just injecting it right into the mobile phase. Right? So the answer would be GC. Okay. Keep going. Miriam. She says LC for the next one, right? So now we're talking about number 2. LC, GC, or both? Yeah. What does quantitation mean? Numbers, getting the amount. So many parts per million or whatever. Right? You're after the concentration. Okay, keep going. Kathleen. Oh, I didn't write both. You got to write both. Okay, keep going, Kathleen. She says LC. You agree? I think they both can have great resolution. But it says better. So you really do have to pick one. GC is a gas, right? Look at a liquid, man. Dang, those liquids, they diffuse, right? And it's a liquid. A gas, look how sharp you can make a gas peak, right? Gases can really high intensity, and you can really get really GC. Okay. Okay, we're at Adriana. 4 has a mobile phase that moves through the stationary phase. What do you think? If you say GC, does LC have a mobile phase that goes through the stationary phase? Yeah, so it has to be both. Okay. Separates mixtures into pure components. Everybody agree, both? Yeah. Yep. That's chromatography. Stationary columns may be reused. Jeff. Stationary columns may be reused. LC. GC.
I thought it was LC because you have that little guard.
Yeah, we have that little guard column, so we can definitely reuse them in LC. Can you reuse that big, long capillary column in GC? Yeah. If you couldn't, this would be totally impractical, right? You have to, it'd be way too expensive and way too much work. Rapid results. Anna. Yeah, you could screw up on either one, I guess, but upon injection, Casey, sample is immediately heated above boiling point. GC? Yep. Extremely reproducible results, Pedro. Both. Better be. There's no point to all this. Difficult to detect co-eluting peaks, Amanda. Difficult to detect co-eluting peaks. If you answer LC, see if you can answer the question also for GC.
GC has the different types.
I mean, it's kind of a hard question, but you can have co-eluting peaks, right, in anything. So I think it's both, but it might be worse for LC, but I would answer both. High cost of equipment, Kat. Yeah, they're both pretty expensive. Uses capillary columns, John. GC. Operation can be complex and require training, Nyla. I think so. They haven't got that simple. Only for molecular weight analytes, bigger than 1,000 grams per mole. What would you guess there, Miranda? She guessed right. LC. Why? The bigger stuff gets. Oh, here's a good. If you remember your general chemistry really well, if you remember this, what force is it where you get this bigger and bigger and bigger and bigger stuff, and it starts interacting even better, right? Intermolecular forces, higher boiling points, higher everything. It was London, or so the V, van der Waals, right? So stuff gets so big, you have to heat it so dang high, it's just going to eat up on you. It's going to decompose, fall apart, caramelize, whatever word you want to use. So you can. It only works for LC, for stuff that's that big. That's right, remember, what was the percent? Only what percent is good on the GC? 20. Okay. Column is at a temperature that is less than the boiling points of the analytes. LC? Could it work for GC? It's a common misconception. I've dealt with it more than once with instructors and faculty. Once you get it in, once you vaporize it, it's a gas. It's going to blow through the column. You don't need to keep it really hot all the time. You can lower it as much as you want just so it doesn't condense into a liquid. If you keep it moving, it'll be fine. So it's both. You don't have to, right? I mean, you don't have to be. Typically, different analytes interact differently with the stationary phase. True, yeah. Who has it? Erica? Both? Everybody agree? Both? Yeah. We skipped Kimberly.
No, I answered.
Did she? Okay, we're on Jamesa then. Typically, different analytes interact differently with the mobile phase. Typically, different analytes interact differently with the mobile phase. It probably has more to do with LC than GC, but it doesn't have anything to do with either one. The mobile phase just has to push stuff through, right? Now, you're right. There's more interaction on LC. So if you're going to answer this and pick one, you'd probably pick LC. But it really doesn't matter. The mobile phase just pushes things through. LC, it just has to dissolve, though. Okay. You can routinely analyze large molecules like proteins. Back to the back. Miriam. Why is it LC? It's that darn molecular weight limit thing, right? Okay. Resolution occurs through adjusting temperature. Kimberly, louder? GC. Resolution occurs to adjusting mobile phase composition. Everybody? LC. Commonly uses high pressures during elution. Everybody? LC. Technically, you probably say HPLC. Okay, whatever. Commonly uses packed columns. Yeah, but which type was that? LC. GC, 99.9999% of the time, they use what type of columns? Capillary columns. Are they packed? No, they're an empty tube in there, right? Well, they little liquid layer, but can have a mass spectral detector. Just a detector. Slap it on whichever one you want, right? Okay. So have a good day.